This is the mission 48, organized by Habitat Marte, analog station. Today we will have the presentation of Davi Souza from Brazil, and also I believe that Marlon Mello will also collaborating with the topic related to the greenhouse and food production system. And then thanks so much, David, for your participation. You are welcome to start your presentation. Thanks so much.
Thanks, Professor Julio. Another time, I would like to say thanks for the opportunity to be here presenting some of my knowledge related to the greenhouse. And then another time, good talk to the all crew. I will be presenting about the greenhouse facility. I was designated to be the greenhouse chief. And this is the mission 48, realized in a virtual way. And then I'm Davi Souza. Nice to have all of you here. These were the topics that I will be passing through and be presenting now during this time. Just to be really quick, our mission goal is to provide some protocols for each facility, and then I will be exploring more of the last topics related to the protocols and routines and protocols of safety, activities of occupancy and entertainment. The food microproduction will be a little bit different. I will be passing through the presentation too, and also for protocols for 3D printing. Some initial considerations about space greenhouses is to achieve one big challenge, that is to grow crops in space. As we already know, it's not as feasible as we think to grow crops in space. Some experiments on ISS shows it a lot related to the effects of microgravity, radiation, and many other issues that we may be facing there. But if we are considering an habitat on Mars, we need to provide an artificial ecosystem that will be allowing us to grow crops as much as similar as we have here on Earth. And then we will be providing some local or in situ food production. The most goal is to meet the demand for food on long-term manned missions or long-time missions to arrive on Mars and to keep the establishing process on Mars. And also, this food demand need to provide necessary nutrients for astronauts' food. And then when we want to achieve these points, we need to have efficient and resilient structures for food production. That will be promoting favorable conditions for the cultivation and growth of plants. And then just a quick introduction related to the environment. We need to have circular environments and ecosystems with closed loop systems and thermal regulation to have the better kind of approach inside of this structure. Again, the initial considerations. I bring this picture that I took it off from this paper, minimal number of settles for survival on another planet. And then we have this pyramid with many important approaches to be considered in the most part of the habitat, but mainly in the greenhouse structure. That we have some industrial systems and machineries and technologies, and also energetic systems. Also some building tasks or implementation of structures. And all of these we need to integrate in one ecosystem with a favorable atmosphere, similar as much similar to Earth, that will have living organisms such as humans and plants. And considering the human living there, human habitation on Mars, we need to consider also in this settlement the human factors that will be the top of the pyramid. And the most important thing when we want to achieve the resilience on Mars. In the previous mission, we have the challenge. We had proposed a challenge to Yash Radot, and then he presented to us a design, a visual concept of an habitat on Mars. And then this is the visual concept that he proposed to us. As you can see, the greenhouse is like in the middle of the stations. This would be the better logistic approach, because we would be near of engineering facility, sanitation center, main station, and health facility. And during my presentation, I will be explaining some interesting points that will be made in the relationship between the greenhouse and with the other stations, the other facilities. Again, just to present a concept, the proposed concept by Yash, a 3D concept, as you can see there, the greenhouse facility again, and also the sectors. The idea I have modified it here because he proposed a general concept, a general sector for the other facilities, and then I have modified these sectors to be more useful and be presenting here other interesting topics to all of you. And then we have 2 floors with an area with a circle. The base circle is about 80 meters diameter that would be provided that are that could be useful to be put into the rocket as a payload. And then this structure, we have 2 floors. The ground floor will be the cultivation area, the laboratory, and the workspace of the facility. And in the first floor, we have the social entertainment area and also the dorms, the sleeping and toilet too. So here is my proposal for the sectors of the structure of the facility. I will be pressing first. I will be explaining something related to the ground floor first. As you can see here, we have these black parts are the airlocks, and then we have some airlocks to go to the other facilities, and then we have a hall here that will be like a circulation area. And as you can see, we have some vertical gardens, the green walls here, and in the hall we have like some glass that will be exposing the plants and providing a better a green environment, that when the astronauts are passing through the greenhouse will not go in the system really, but will be able to see how is the crop development, and also to be more near of the crops too. And then we have the lab and the work area, the processing area, the storage area too, and also in the middle of the system of the facility we will be having the fish tank, and also I proposed here something like two or three kinds of cultivation, that we will be having some algae cultivation, and also the green walls and vertical beds, as you can see there. And another interesting point to be considered is that we have some trails that will be allowing some robotics arms to do the maintenance and the management of the system, to be assisting the astronauts inside of the facility. And in the first floor will be more a social area, and then we will be having the entertainment and social area. for like to have meetings or to have other interesting things that would be providing a better well-being, mental well-being for the astronauts. And the kitchen, the toilet, and also the dorms. As you can see there, I proposed 2 dorms. I will be explaining why I proposed that. And now explaining this, the number of astronauts and positions that we have there, we need to have the greenhouse. The idea is to have two permanent vacancies. That would be the greenhouse manager. Considering that I'm the greenhouse, I was designated to be the greenhouse chief. I will be providing to you some guidelines as the greenhouse manager, and also the technical assistant. And also we will have a rotating vacancy or position that will be, I will be explaining what I proposed here. That the visiting assistant would be like one member of the whole crew of the other facilities that will be going, will be selected on a rotating basis to go to the greenhouse and know, to have the minimal knowledge for about food production, about the greenhouse management, maintenance, and other tasks in case of any need. Because if the technical assistant or the greenhouse manager get some ill or is not allowed to be there doing his tasks, the other crew members would be there, are able to be there and assisting in the food production in the whole environment. And also a complementary objective of this vacancy, the visiting assistant, is to provide an Earth-similar environment and contribute to the crew's mental health. So we'll be providing, we have different stimulus and also different tasks for the whole crew, to not doing all the time the same task, the same activities, and then this would be in a rotating basis, of drawing to maybe by day, maybe by week, and then this don't matter at all. It depends on the people and also the necessity of each facility. The duties, the responsibilities would be more related to the decision making, system management, the greenhouse maintenance and cleaning, and monitoring the water quality. This is a really important task. Also to plan and establish a cultivation schedule, analyze environmental data and crop statistics, plan the dynamics of food cultivation and harvesting, and other operational procedures. And then these responsibilities could be divided into the greenhouse manager and the technical assistant. Related to the quantity of resource that we will need, and we need to consider that the dimensions of the system for energy supply, water supply, heating, and air conditioning will be determined by the number of inhabitants and also the amount of vegetation. We need to have a collaboration between both. And we need to use all of the generated biomass, including alternative sources such algae or insects, and also for the maintenance of the production system. And also have, I think, when we want to achieve a self-sufficient, self-sustainable habitat, it's important to establish some indicators. And then I propose 3 stages here. When we have the deployment of the environment, when we need greater demand from Earth resource, then when we achieve the sustainability, and after that, when the habitat becomes self-sufficient and self-sustainable. Sorry about that. I have forgot the self there. And when we have the independence of resource from Earth. Just to present you a quick, a brief introduction related to the quantity of resource, I bring this paper here to present you. The name of the paper is the Greenhouse production analysis of early mission scenarios for Moon and Mars inhabitants. And then, as you can see there, we have two principles of cultivation that's called in-phase and also shifted cultivation. And the difference between them is the in-phase cultivation, we have, as you can see, we have the T+0 time that we will be starting all the cultivation process, like we will be implementing in the modules or in the areas, in the nurseries. We will be implementing all the crops at the same time, and then the period of harvesting events would be like by blocks at the same time. And the shifted cultivation, we have different times to start the cultivation. As you can see there, the T+0, T+7, and after a time we will be having some harvesting events that will be like separated events. And considering this, we have this kind of sorry. We will have for a crew with 10 members. We can consider like different grams per day of biomass consumption. And just to present you some ideas here in the first part, we have 1.5 kilograms per day, and then the biomass consumption will be regular, and also. And if we consider this quantity of resource during a period, the total biomass storage status will be increasing. And in the other hand, we have 2.1 kilograms per day of biomass consumption, the same regular as the other. And considering this approach, the total biomass storage status will be getting low, and as you can see there, the difference between both. And when we consider the necessity of food demand, the food demand of the astronauts, we can't consider just 1.5 grams per day, So the most appropriated approach would be with higher amounts of biomass consumption. And just to present the results of this research, we have the two approaches, and I will be, just to have an idea, the red line is the full consumption, the blue line is no consumption, and the green line is the partial consumption. Then we will be considering the partial consumption, that will be like the ideal condition. And as you can see there, the shifted cultivation approach, during a period, we will have like more viable crops and more viable food, and during the days. And this graphic was considering the 2.1 kilograms per day. And in the shifted cultivation approach, we will be having more days than the IPC approach. And as you can see there, comparing the 37 days and 81 days, but if we consider that the availability of resources are higher, this would be the most better conditions. And considering this quantity of resource, as you can see there, this paper considered the number of members, 10 astronauts. We have a daily consumption of 2.1 kilograms, and a week consumption of 14.7 kilograms. And doing the calculations there, we have about for a week, like 1.5 by person, about 1.5 kilograms per astronaut. And considering the amount of 2 liters of water by person, during a week we'll have like 21 liters of water. And considering the greenhouse facilities, we need to achieve some functionalities, such as enhance the system reliability, achieve an optimal growth and high yield, have a good environmental control, and also a good crop monitoring. And then with two activities, we maybe have some possible technologies that will be implementing the greenhouse. that is hydroponics, aquaponics, or also aeroponics too. Vertical garden, as I proposed in the concept, algae cultivation, artificial lighting, sensoring and automation, robotics, and also assisted with artificial intelligence, machine learning, and computer vision. And in this picture, as you can see, is a proposed, it's called Sirona environment, is a greenhouse approach considering like robotic arms and also different cultivations areas, as you can see there. So considering the technologies, we need to have support technologies that will be assisting the crew and also the two members inside of the greenhouse to doing the most part of the tasks during the protocols. I will be mentioning this again. But as you can see, we have some ideas of integrated farming tech that will be integrating vertical farming, environmental monitoring, automated computer vision, autonomous robots, and also in others approaches too. And just to present you some pictures related to it, we have like in the left top, the top left corner, we have the fiber optic to do the greenhouse lighting, and in the bottom left corner we have some robots, assisting the green walls, the vertical, also vertical farming, as you can see there, maybe associated with the use of computer vision, as you can see in the other picture with the tomatoes, to see if we have a healthy tomato, a diseased tomato, or if we have like a tomato ready to be harvested or something like that. And then this robotics would be assisting in the maintenance, management, sorry, and also in the cleaning of the structure. And just to present you, as I mentioned in the concept, we will be having some robotic arms with some trails, and then this would be a nice approach, a visual approach of implementation. Related to the habitat support, the greenhouse will be providing to the whole habitat some economic practice, and also providing some awareness and education guidelines and education activities and guidelines for plant growth and instructions for better management of the micro food production. And then this is a really interesting approach that I consider for the greenhouse, that we have the levers of the greenhouse, that would be the crops, the production of food, or any other the levers, and these things that will be producing will be promoting the well-being of the astronauts, like the nutritive meals, and also the mental well-being, like considering the human-plant interaction. And with that, we will be providing for the crew some creativity, and this creativity will be really important when we consider like problem solving or technologies development. And then if we have a creativity, we have a creative astronauts, it will be increasing the possibility to improve or develop new technologies in the habitat, and using also in situ resource utilization, considering in situ resource utilization. And these technologies will be assisting in the food production and other deliveries of the structures. And considering the habitat support, so I divided, as I mentioned, that I divided the protocols for food micro production, because the greenhouse will be providing the extensive food production, and these habitats, this protocol will be more related to the habitat support. And then we will be considered the well-being logistic for the astronauts, the food distribution, reduce workload, and also avoid risks in the other facilities. And as you can see there, so some routines are related to management, maintenance, recycling practices, and also harvesting and processing. And the activities, the tests that will be developed consist in some analysis, diagnosis, to ensure the circularity of the system, to assure the fidelity of the methodologies, orientations, and detect some possible failures. And as I mentioned earlier, the support technologies would be assisting on the most part of these processes in the protocols. When we have defined activities, defined routines and tasks, it will be more easier to implement some kind of technology assisted with robotics. Some guidelines for Earth. We have the spin-off technologies that are some technologies that we developed through space that could be implemented on Earth that would be assisting in our providing any kind of solution for Earth. And then some guidelines will be associated with efficient crop water usage, water recycling to sustain life, and develop new abilities to grow food on Earth. And just to present you two concepts, two projects, prototypes on Earth, we have the biohabitat greenhouse in Habitat Marte, and the lunar greenhouse prototype in the University of Arizona that Janine mentioned in her presentation yesterday. Both are controlled environments to produce food, and then to see how this kind of system could be implemented on a space environment, a space habitat. Related to the greenhouse of Habitat Marte, we have the technologies as we presented in the live. We have aquaponics, sensory and automation. Some routines are related to water management, water flow and quality, analysis of crop growth, crop disease or pests, collect environmental data, fish health, biomass, and recycling practices. Marlon and Sarah, I don't know if they are already there, but they had the opportunity to see how is the implementation, to have a hands-on there and see how all these routines are applied in Habitat Marte. And some data that we collect there are related to temperature and relative humidity of the environment, and also water temperature, the pH of water, ammonia, nitrate, and visual analysis such as turbidity and water flow, as I mentioned in the live. Some protocols that we have there in Habitat Marte, as you can see, there are protocols related to food production, as we have food cultivation, food system maintenance, greenhouse building, greenhouse building, space food systems building, food harvesting, processing, evaluation of contaminants and plagues, and also processes to food waste, harvesting and cooking, and also related to the reuse practices. And then just some routines that we have there in Habitat Marte related to the management, as I mentioned, water circulation, quality of water analysis. I will be quick here just to present you some interesting parts. We have it's interesting related to the management, the water circulation, the water quality, also the partial water exchange, because the water, considering the aquaponic system, the water is the main resource that guarantees the balance of the system, of the ecosystem, food ecosystem. Related to the maintenance, other interesting are the general observation and repair of the infrastructure. See if we have any contaminants or plagues or ants or any problems related to the crops, and also some cleaning activities and removal of dry leaves and dead plants. And related to harvesting and processing of food, like we have the selection of the crops the crops that are healthy to be consumed. The pruning of plants, examining to see the weight of the collected food, and also cleaning the water and destination for consumption, cleaning with water and destination for consumption, and some fish selection, and also slaughter and cleaning of fish. And then, as you can see there, these are some routines. These are some pictures related to these routines that we have there in Habitat Marte. We have the crop to monitor the crop health, to see to do the fish observation, macroscopic observation, and to see how is the health condition of the fish. Water quality analysis, fish processing. Here we have some activities to take the tilapia fillet, and also here our harvesting process, a harvesting event that we had there, collecting some lettuce. And other protocols are related to the waste reuse. This is also some protocols that are interesting for the sanitation center, like some practice related to the sanitation center. We have there implemented in Habitat Mate. We have the application of the roots as a substrate for the other system. As you can see in the right picture, we have, it was an experiment proposed by Professor Julio to take off these roots of a dead plant, and then we had an amount of organic matter that could be useful to be applied, that was useful to be applied in the WC system. And also reuse of organic matter, as I mentioned, water, as I mentioned, and as you can see there in the left picture, after our cleaning activity, we take the water with an amount of organic matter, and we store this water to reuse it after 30 days in the system, and do the water replacement after the cleaning. As you can see here, here is Dalmo. Dalmo is aquaponic specialist that helped us in the implementation of the aquaponic system in Habitat Marte. And also the proper destination of the remains of cooking and harvesting activities. And then, sorry. And then, related to safety and also disaster protocols, we need to have some guidelines related to fast isolation, evacuation, food recovery, and also keep ergonomic in the habitat. As you can see there, in case of isolation, we should analyze the available resource and calculate the viability of this existing biological system, and establish an order of the activation of that area. And related to the evacuation, we need to guide the other members of the mission regarding the maintenance and optimization of the food resource available in each emergency food production. And then this is also associated, will be implemented in some kind of habitat support in the micro-food production. And the food recovery, to monitor and tabulate the responses of the cultivars to emergency situations and perform the inventory of losses and recovery schedule. And to keep the ergonomic there in the system, we need to maintain as far as possible the viability of the production systems, identifying and analyzing the critical points of the structure with some respective response to emergency situations, and tabulate all of this data. Also some activities of occupancy and entertainment. As I mentioned in our first meetings, it's important to all the facilities to have an environment-friendly design. As I proposed it in my concept, we have the green walls and also social areas with a lot of greens, and also to provide some alternative routines for the astronauts. One example would be some cooking classes. I mentioned during our visitation to Habitat Marte that I really like to do some sushi, and using the tilapia would be a good choice to implement this kind of approach. Also, the planning of the cultivation of the crops, of the plantations, we have contributions from the entire team to see what the preferred meals of each astronauts, and then we will be producing, and will be like making a comparison of sorry, I don't remember the word now, but just to compare how could be, what would be the best crops, and to see what are the preference of the astronauts. And related to the human plant interaction, as I mentioned, related to the well-being, the creativity, there will be a schedule for using the greenhouse as a social space. As I mentioned, we had the hall that the astronauts would be circulating, of the astronauts of the other facility would be circulating, but in some scheduled datas and scheduled moments, we would be having like other activities inside of the greenhouse and also in the social area or something like that. And related to protocols for 3D printing, and I added to some custom manufacturing. We have the algae cultivation, that is a possible use that has a lot of protocols related to it. I won't be presenting any routines because I'm not a specialist on it. But the algae cultivation will be providing edible biomass. As you can see in the picture, we have a cereal bar made with spirulina, and also this cereal bar was produced by the algae cultivated in the ISS. It's like a meal that the astronauts has available for them there, and also some fish food, and also the carbon dioxide to oxygen conversion, fluent treatment. This is also, the algae cultivation is also important for the water treatment and also some water recovery systems. And then related to food production with 3D printers, we will be providing some diversity and nutritional stability. We'll be providing attractive foods with more acceptability between the astronauts. And also with resource saving, will be like designed meals, like, and then we will be like saving other resource and other biomass that would be useful for other necessities. And also related to the custom manufacturing, we have plant-based manufacturing related to bioenergy, biopharma, and biostructures. On the bioenergy, we will be providing, we will be generating energy with some waste of the organic matter using biodigesters. Related to the biopharma, we would be using the plants as raw material for medicines and phytotherapy. And biostructures, an example is the bamboo. As you can see in the picture, we have a vertical garden made with bamboo, and then we will be producing in the greenhouse other structures that will be useful for the greenhouse or also for the facilities, for the other facilities too. And related to tools manufacturing, we will be having some modeling of structuring elements with 3D printing and other structure. I bring an example as I told you. This is an example of optical fiber based on agarose algae. That this optical fiber is useful to be edible, is biocompatible and biodegradable, and have many applications in medical field, such as phototherapy and biochemical detection. And that's it. These are my reference. Thank you very much for your attention. and I'm open for questions and comments and suggestions. Thank you very much.